Hello everybody, my name is Alexander Felfernig from the Graz University of Technology. The title of this talk is Direct Debug, so it's about the automated testing and debugging of feature models, and the work presented here is joint work of Viet-Man, me, Mathias from Siemens, and David Benavides, Jose Galindo from the University of Seville, and Tran, she is also from the Graz University of Technology. So the major topic of this talk are feature models. Feature models are typically used to represent variability and commonality properties of different software artifacts. The software artifact we are talking about here is a survey software. It's configurable, so me as a customer, I'm able to specify which features should be included in my personal variant of the software. So feature models consist for sure of features. These models typically have a hierarchical structure, and there are different types of relationships that can be used to specify additional properties that have to be taken into account. So for example, we have an optional relationship between features, which means that here in this example, the statistics feature could be included in a configuration, but it's an option. We have a mandatory relationship, so every instance of the survey software should have a question answering feature, otherwise the software doesn't make sense. We have an or relationship. In this context, this would mean if we have to select a question answering instance, we could choose multiple choice, single choice, or both, and we have alternative relationships which basically represent an XOR semantics. So in addition to those basic relationships, we have so-called cross-tree constraints. Excludes means that these two features must not be combined in a configuration. So this is not possible, so these two features exclude each other. And then there is a second cross-tree constraint which specifies the requires relationship. So A/B testing requires the inclusion of the statistics component. Such feature models can be translated into a corresponding formal representation. So for example, there's a constraint satisfaction problem. So we can do constraint solving or complete different constraint solving tasks for feature models. So the problem, and this is the major problem we deal with in this presentation, is that feature models can become erroneous, so for various reasons. So for example, due to missing domain knowledge or kind of cognitive overloads, we include faulty constraints, faulty relationships in the feature model, and if feature models become complex, it's extremely important to provide corresponding debugging mechanisms that point out automatically so which parts of the model are basically responsible for the faulty behavior of the model, and that's the major focus of this presentation. So what you see here on this slide is the standard way to analyze feature models, to test feature models. So we have the feature model, and then we have kind of different analysis operations. So we can test if every feature in the model isn't dead. So there exists at least one configuration where this feature is active. So this is a very basic example for a testing operation for the feature model. So this analysis operations are doing a kind of defect analysis of individual patterns, and already provided an example. So a dead feature is something we do not want to have, so we have to test for that. Other examples are void feature models. So it shouldn't be the case that the feature model doesn't allow to calculate the solution. So these analysis operations basically support individual tests, but we are interested in something that is integrated, that given a set of tests, we want to figure out where are the regions in the feature models that are responsible for the faulty behavior of the model. So what is the basic idea of our solution? So we have a feature model, in this case represented in terms of a a set of constraints. So I told you that it's possible to translate feature models into a corresponding constraint-based representation. Then we have different test cases. Test cases specify intended and unintended behavior of a feature model. So we have in this situation, it's just shown here. So the red ones, they basically induce a conflict with the feature model, which means that this test case specifies intended behavior, but the feature model doesn't support it. So we have a test case that induces a conflict, and we have another test case that induces a conflict. The other test cases are consistent with the set of constraints. Test cases can come from consistent configurations, can be manually defined, or also generated from specific fault models. So we have conflicts that are induced by the test cases. So we can use a kind of diagnosis approach that resolves the conflicts, and the result of a conflict resolution is then called a hitting set or a diagnosis, which means that, for example, in our simple example, if we change or delete C3 from the knowledge base, then the whole test suite becomes consistent with the knowledge base. So consistency is restored. So test cases help to specify the intended behavior of a model. And what we basically do, and what we show in the paper, is how does an efficient algorithm look like to determine those hitting sets. That's the basic idea of our. So as mentioned, the direct debug algorithm cannot be used to determine hitting sets or diagnosis. So we see a very simple example here. We have a set of constraints representing the feature model, and we have two conflict sets here induced by a given set of test cases. So the basic idea of this direct debug algorithm, you see this here, is divide and conquer. So divide the constraints in the middle, test if there are still test cases that are not supported or where there is an inconsistency. Do again repeat the divide and conquer until we achieve a consistency, which means no test cases are violated, and then we rebuild the partial model. So we add the half of C3, C4. We see C3 as an individual constraint, as a singleton induces an inconsistency. So C3 must be part of the diagnosis. So we have already identified one such element. We can move on. We can add C4. There is no inconsistency. We can add the first half of C5 till C8, no inconsistency. And finally, we add C7 and C8 and still no inconsistency. So what direct debug calculates is a maximum satisfiable subset. The complement of that is a diagnosis, and this is what is relevant for us, because C3 is potentially the source of the problem of these conflicts between the test cases and the feature model, or the CSP derived from the feature model. So direct debug is extremely efficient and applicable in real world, in industrial scenarios. For reasons of time limitations, I will not discuss the evaluation here, and basically refer to the discussions in the ICSI paper. So to summarize our work, feature models, especially complex feature models, can become error-prone. What we need in such scenarios are intelligent testing and debugging techniques that really pinpoint the faulty constraints in the knowledge base. Existing approaches do not support such a pinpointing. Direct debug does this, and from our point, the major contribution is integrated testing and diagnosis based on divide and conquer, which is easy to develop and to integrate in existing feature modeling environments. Further work will include optimizations of direct debug, and also the inclusion of machine learning concepts to order constraints in C, because this has an impact on which diagnoses are returned by the algorithm. So thank you very much for your attention. I hope that you have a chance to also take a look at the paper, and maybe there are also possibilities for cooperation. And for sure, I hope that you have plenty of questions regarding the algorithm and our work. Thank you very much.
Hello, welcome to the Q&A session for the paper towards automated testing and debugging feature models. I have here Alexander, Jose, and David that can answer your questions. And as you know, please write your question in the chat room. And this is a near presentation, and we have only 5 minutes for this stage. But then the authors can join you in the discussion room. So we have 4 minutes now. Just to fill the empty space, Alexander or the other, if you could clarify this difference. In your presentation, you go from diagnosis to debugging, and I was not clear about what is really the difference. You said that your tool makes diagnosis.
Okay. So the question is the difference between diagnosis and debugging.
Of the feature model, yeah.
I would say that the diagnosis is the technical basis. So it's a technique to support debugging processes of all the feature models. Yeah? And the major advantage of diagnosis is that it's able to calculate minimal regions with these 40 feature model elements. Okay. And this is a kind of debugging support for a knowledge engineer who builds a complex feature model. That's the basic idea.
I see. And do you propose when 2 minutes? So a quick answer. When is the algorithm to be applied? Is it triggered when there is a problem, or it is something like regression testing that you apply at each evolution?
So it's the algorithm can be triggered in different contexts. So the extreme case is that the whole feature model is inconsistent. And the algorithm or a variant of the algorithm would indicate which constraints of the feature models are responsible for the faulty behavior, for the inconsistency. In the version that is now included in the paper, the approach is, let's say it's similar to regression testing, but it's not really regression testing, because all the test cases that are provided are taken into account at the same time. Okay, so the diagnosis basically indicates a set of constraints that have to be adapted or changed such that all the test cases are satisfied. That's the basic idea. So it has something to do with regression testing, but it's not regression testing, basically. It's automated debugging.
Okay. So you have 1 minute. If no question appears in the meanwhile, you could just take the time to talk about action that you are taking now.
Yes, so as also is indicated in the paper, there are different directions in future research. One important direction, a really important direction from my point of view, is to deal with this topic of where do the test cases come from. Okay, so this is something in this paper we did this a data set synthesis. So these were not real world test cases. Evaluation purposes, what we did is the synthesis of the test cases we use for evaluating the algorithm. And in future variants of the algorithm, we will heavily focus on this aspect of including test cases from already existing configurations, automatically generating test cases from well-founded rules. In the feature modeling community, there are different approaches to define well-founded properties on feature models. We will exploit this additional knowledge to automatically generate test cases. And one very important aspect from my point of view is the ranking of the diagnosis. And, this is an important topic for future work.
Hi, everyone.